Okay, so we are resuming. This is now we have Chris and then Elias, and then Chris Elias again in the afternoon. So the usual 45 minutes. I'll give you the time. Okay.
Okay, so while you find your feet, just to remind you last time what we did, we went through solenoids, we derived the solenoid transfer matrix from the Hamiltonian. It's coupled between X and Y, so that means X and Y mix during solenoid transport, and you can rotate the transfer matrix to decouple X and Y, and then solenoids are focusing in both decoupled horizontal directions. There exists a single Betatron function that evolves with this second order differential equation. And if this second order differential equation does not yield a real solution, then that means that we're in a resonance, linear resonance. Solenoids conserve canonical angular momentum. So canonical angular momentum is this thing. So that's xpy minus ypx, which is like the kinetic angular momentum plus a term coming from the magnetic field B0. And the consequence of this statement is that if you're in a solenoid field, typically you will have a kinetic angular momentum, which is proportional to Vz. Okay. So right, so I'm going to go through now for lecture 2. I'm going to talk about emittance. So we'll get into cooling. So first of all, I need to tell you what emittance is, and I sort of mentioned it on Monday, but I'm going to go through it in a bit more detail. So I'm going to talk about second moment invariance, which I started yesterday, but I'm going to do again. Then I'm going to talk about how we get transverse emittance reduction and how cooling reduces transverse emittance. And then I'm going to talk about how we get longitudinal emittance change, and that's using something called emittance exchange. Okay, so let me start off with the mean of a distribution. So the first moment of a distribution is the mean, of course. So that's just, as you know, I'm sure, you take the sum over all particles, divide by the number of particles, and that gives you the mean. And we can transport the vector of means just using the transport matrix. So what I've done here is I've just written out in longhand the matrix multiplication equation, and then the trick which I'm going to do is, because multiplication is commutative, you can move this thing outside of the sum over all particles. There's no particle index on this. This is the, let's say, the position or the momentum. So every particle has a different position and momentum, but every particle has the same transfer matrix element. So you can just move this outside of the sum, and that means that you can you can just take the transfer matrix outside, and you end up with the mean vector of means is equal to the transfer matrix times the vector of means at the initial state. Okay. So the point is, you can use a transfer matrix not just to propagate a single particle, but to propagate the entire ensemble of particles. So the center of a bunch, the mean of a bunch, transports just like it was a single particle, which has the position. And you can sort of, if you imagine that you have some y distribution, if you imagine you squeeze your distribution down and down and down to the point where every single particle has the same position or momentum, and then of course all of those particles will transport in the same way. So it sort of makes sense in that context. Okay, so now let's consider the second moment, covariance. So we define the second moment in this way. Again, the sum over all particles of the product of two of the phase space vectors. So position and momentum, for example, are a position and a position, divided by the number of particles again, of course. So for example, the covariance in x and px is equal to the sum over all particles of x times px. Then if we define the covariance, so what I'm going to do, I'm going to define a matrix which we call the covariance matrix. So that's the matrix which has all of these covariances for all of the different phase space coordinates inside it. So it's a matrix V, and the elements Vij are just a covariance of Ui times Uj. So x, so it'll be x times x as the top left-hand corner, and then x times px, and then x times y, and so on. Okay, so now we want to find out how we transport that. So we want to find out how we transport the second moment now. So we can do the same trick which we did with the first moment. So we take the we take the final covariance matrix element. So we're just going to do the initial element times the transfer matrix, just like we did with the first moment. And then we're going to juggle the order in which we take these summations. Again, we're using the commutation relationship. So we can take these matrix elements in and out of the bracket. So if we put a bracket around this summation here over all particles, well, this is the covariance of the initial coordinates. We have a transfer matrix at the beginning. So we just move this transfer matrix and move the particle sum inside, move this transfer matrix outside. And then we're going to have this transfer matrix element at the end. And the point is, so this blue thing looks like matrix times the input covariance matrix. And then this thing actually looks like the transpose of M times this. So it's like so we can transport second moments using this relationship here. Okay. Good. Okay. So now I have a question for you. So the determinant of a matrix, you may remember from your high school, I guess, or undergraduate, the determinant of the matrix, a product of two matrices, is det A times det B, is the determinant of AB. And the determinant of a matrix is the same as the determinant of its transpose. So, and M is a symplectic matrix. So that means that it obeys this relationship here, where J is the symplectic, this symplectic matrix. So the question then, given those three facts, can you tell me what the determinant of M is? Go on. Yeah. Plus minus one. You're right. It's plus minus one. Yeah. That's it. So and in fact it's positive. So it's positive one. But yeah. Okay. So then, given that the determinant of M is 1, what can we say about the determinant of V, this covariance matrix? If I flip back to this relationship here, potentially. Yep, the determinant of V is constant. That's exactly right. Okay, so that's an important relationship. And we're going to find out on the next slide, probably, that the determinant of V is very closely related to the emittance. Okay, there you go, on the next slide. So the RMS beam emittance for a 4D beam is calculated by doing the determinant of this 4D transfer matrix, then we take the fourth root. So that's the mathematical, how we calculate it mathematically, and because determinant of V is conserved, emittance is conserved. Well, I probably won't. I probably will not, or not much. So yeah, we can do that as you prefer. Okay. So that's the mathematical formulation. I wanted to explain a little bit more about the geometrical interpretation of that formula. So the equation for a 2D ellipse is given by this expression. So an ellipse in my 2D variables u1 and u2. So this is V, the covariance matrix elements V. So we can write that down as a 2D matrix equation. We can write that down as U vector transpose times V to the minus 1 times U vector. And this is actually the equation of ellipse, and the area of that ellipse is pi square root V. So actually what we can interpret this emittance thing as is actually it's the area of an ellipse which is sort of moving along with the beam and expresses the size of the beam in terms of a sort of 1 sigma size of the beam. And it's and in fact all of the particles which sit, any particle which sits on one of these ellipses, that ellipse will always have the same area. So it's not just this sort of 1 RMS distance, actually, that you have this whole ensemble of ellipses, similar ellipses moving along with the beam, each of which is invariant. So that means that the particle, with each particle, you can associate a single particle invariant, which is the area of this ellipse. So we can calculate this. We can write down this quantity, which is the sort of single particle emittance, sometimes called amplitude, of a particle, which is for the ith particle here, so the normalized emittance, which was this thing on this slide, times this phase space vector, V inverse phase space vector. There's a little transpose up there as well. And actually, just to prove that this thing is invariant as well for any particle, we can again go through the same thing of doing transport. So let's say U transpose just transports as M times U all transposed. When you transpose, you reverse the order. Then V, we know, transports as M2 times V times M transpose. And then we have M, which transports just like your U, which transports using the transfer matrix. Then we take the inverse. Well, we flip the order when we take the inverse. That means this M transpose cancels with this M transpose. This M inverse cancels with this M inverse. We end up just with this expression. So the whole thing's conserved. Okay, people sometimes talk about 95% ellipses and 99% ellipses. So that's the ellipse which contains 95% of the beam or 99% of the beam. People also sometimes talk about 3 sigma ellipses and 5 sigma ellipses, which is the ellipse which is 3 sigma away from the beam center or 5 sigma away from the beam center. The only thing I just want to express a note of caution that actually if as experimentalists, you know chi-squareds very well. So this, if for a Gaussian beam, this looks very much like a chi-squared. And as you go up to higher dimensional spaces, you've got to be a little bit careful about how things behave because a 3 sigma beam in a 4-dimensional space contains a different proportion of the distribution to a 3 sigma beam in a 2-dimensional space. So just bear in mind that little note of caution on how you interpret these 95% to 99% ellipses. Fine. Okay. So this is actually this is a plot from the demonstrator lattice. So I wanted to just sort of try and so I want to sort of discuss what's going on in this plot. So you have position, horizontal position, and horizontal momentum here. And actually for this, because the demonstrator lattice goes into a solenoid, then comes out of the solenoid, what I've done is every time we go out the solenoid, I'm plotting the horizontal position and horizontal momentum. So our beam is coupling as it goes through the solenoid. It comes out of the solenoid, it's uncoupling again. So every time I make this, I plot a point, the particle is only in xpx because it's going into the solenoid and out of the solenoid. So what I'm then doing is looking at the particle every time it goes into the solenoid, every cell, and I'm plotting the phase space position. And so what you can see is that this particle is moving round along an ellipse. So exactly what we've been talking about, this trajectory where particles move along an ellipse in phase space. Each color is a different particle. That's right. Yeah, thank you. So we have a particle in the middle that just stays in the middle. We have a particle slightly higher amplitude, moves around in this nice ellipse. There's something interesting happening here. This particle it's got the same number of turns, it's got the same number of points, but it's in little dots like this. And so this corresponds actually to a tune of 5/13. So this is a very weak, it's sort of like one of these resonance conditions I've been talking about. But in this case, it doesn't excite, doesn't cause us any trouble. But this is actually a 5/13 resonance, quite a weak one. And then we go out, and then out here, something bad happens. This gray one, and that actually corresponds to the half integer resonance now. And so it's just not quite on the half integer resonance, but it's very close. And so bad things are happening here. So yeah, I did put that one in. So if I plot, this is now, I have a few more particles, but this is now plotting the tune as a function of distance, x0, distance from the center. And out here at 30 millimeters, we're crossing this half integer. So if I just go back to this slide, this is just at 30 millimeters. So this is just below the half integer resonance. So just before the half integer resonance. And actually, the reason I colored this particle in gray is it does eventually get lost after a couple of hundred cells, because it's close to this resonance, which we don't like. Okay. So fine. But the point is, particles are going around these ellipses, and when they start on an ellipse, they stay on an ellipse. Okay. So what we can do, in fact, is we can actually plot the amplitude of those particles. So that's what's on the vertical axis. And then what I've done here is I've colored in the histogram. It's 2D histogram. It's falling off the bottom again. That's all right. I'll drop the. Let me just so you can see the axis. This is the total momentum. This is the momentum down here. Let me see. It looks okay on my screen, but not the projector, which is unfortunate. Anyway, it'll have to do. So what I'm doing. So the point I showed you before was actually 0.176. So oh no, maybe it's a bit higher. Anyway, so I took a slice in momentum for that previous one. What I'm doing now is I'm showing you the amplitude of particles, and when the particles survive, I'm coloring it in yellow. When the particles get lost, I'm coloring it in dark blue. So we can kind of we can generate this sort of picture of dynamic aperture, which is looking at where particles get lost and where they don't get lost in the beamline. So particles which have which are colored here are ones which are kept for several hundred cells. So those are accepted by our lattice. Particles which are lost are colored in gray, and I don't plot them on this one. So these corresponds to particles which get lost. This corresponds to particles which are kept. Okay. And then this is plotting the dynamic aperture as a function of momentum. Okay. I wanted to introduce or think about a concept called beam matching. So I have a question. Say I put in this gray ellipse I've drawn onto this picture. I'm going to put particles on that gray ellipse into this cooling system. What do you think will happen to the gray ellipse? Yeah. So somehow I've been saying, these moment invariants are invariant, which is true, but but because the focusing strength varies across the solenoid in a real system, even though in a linear approximation, this ellipse, the area is conserved, when you actually get into a real system, it tends to get messed up. And so what happens is, maybe I will use the board quickly. So if I think about the particles out here, they're going to move at a different frequency to the particles in here. So if I start off with a distribution which is initially elliptical, these ones will move faster, let's say, and this ones will move slower. So I end up with a sort of smeared ellipse. The same for the other side. So you end up getting these sort of galaxy arms forming. So there's this concept of matching, which is where you try and line the ellipse of your beam. When you introduce a beam into a system, you try and align that with the ellipse of your system, the sort of natural ellipse of your system, so that you don't get this sort of smearing out, which eventually will cause emittance blow up and mess up your emittance. I just pulled a plot out. This is a rather exotic lattice, which we were looking at a couple of years ago, but you can see that you can get again x prime in this case. You can get quite interesting shapes when you include fancy magnets and complicated higher order multipoles and things. So matching into a system like this is obviously quite tricky. But this is actually at least a real simulation of a lattice. Okay. So we got to emittance. What about cooling? So I'm going to put a beam through. So in ionization cooling, this is actually the same slide I showed on Monday, but maybe we can see it with slightly different eyes. So we're going to put a beam through an absorber. The beam loses energy in the absorbing material. So the absorber removes the momentum in all directions. And then we put the beam through an RF cavity, and the RF cavity restores momentum only in the longitudinal direction. So remember now we have these moment invariants. Emittance, normalized emittance, is the phase space volume in position momentum space. So if we reduce the momentum spread when we go through the absorber, we actually get cooling. Then the RF cavity reaccelerates. We have multiple Coulomb scattering from the nucleus, which tends to ruin the effect. So when the beam hits the atomic nuclei, it gets kicked around, and that tends to increase the momentum again. So let's go back to this this covariance matrix, this emittance equation V. So this is what I'm doing here. I've just simplified this equation so that it's cylindrically symmetric. So I've taken out the terms with a y in, just because they actually come out here. So this is like the 4D transfer matrix. So how does this emittance expression change? So we can write down that the change in emittance with Z is equal to the change in this covariance matrix with Z. And so then the challenge is to find what this derivative is. So when we go through our material, what we just said, the PZ changes, so PZ is reduced, and we get an angular kick, so theta I squared increases. So these are the two things which are going to change as we go through our material. So we have two derivatives. We have a dpz by dz, and we have a d theta squared by dz. And so we can use so somehow it's more convenient in some sense sometimes to express things in terms of energy rather than have some bits in terms of momentum, some bits in terms of energy. So I'm going to just do a substitution to substitute dpz by dz, write that down in terms of d by dz, and then this beta function, this is the actually this can be written in terms of the variance in x squared. And we use the scattering from atomic physics. So this is just an expression which comes from the the PDG book, rather, Particle Data Group Physics Handbook, which tells you how much scattering you expect for a given material. And so we can get to this expression for the emittance change. This is the transverse emittance change as we go through material. And even I can simplify it further by using this expression for the transverse beta function. Okay, so we got two parts to the equation. We got a negative part, which is cooling, and we've got a positive part, which is heating. So dE dz is always negative, of course. We always lose energy in an absorber. And this is proportional to emittance over here. So if I make this 0, then we can rearrange the equation to write down the equilibrium emittance, where this part is equal to this part. Just rearrange the equation, and we get this expression for an equilibrium emittance. Okay. It's transverse cooling. So what's going on in longitudinal phase space? I haven't really talked much about time energy space, but it's analogous to the transverse case. So in longitudinal phase space, the beam is usually heated. So there are two things which cause heating. That's increase in the energy spread. We get random noise in the energy loss, which we call straggling, sometimes Vlasov straggling. So you can see this is a histogram which shows energy loss. You can see that this has a width. We also have heating due to the curvature in the energy loss. So this is the beta block curve. So it's the mean energy loss curve. And you can see that a low energy particle will lose more energy if we're down here. A high energy particle will lose less energy. So that means that the energy spread increases. This low energy particle gets to lower energy. This high energy particle doesn't see so much energy loss. And so we actually get this longitudinal emittance heating term. Okay. So we can mitigate that using emittance exchange. I'll come to that in a moment. I want to talk about the final cooling system. So this is the last bit of cooling in the muon collider. So what we have here, we just want to get as much transverse cooling as possible. So what we do in the final cooling system is we run with these extremely high field solenoids, so sort of 30, 40 Tesla, and we can go through all of the things I've been talking about to do with beta function. We can actually define a beta function which is matched. So this is so somehow we choose this green dashed curve is the solenoid field. The blue curve is the beta function. So in the high solenoid region, we take a uniform field equation. So that means that beta double prime and beta prime are constant. Bz is constant. That's expressed in this kappa. So that means that we get this uniform constant low beta function, where the beta goes inversely to Bz. And we get down to betas of around 1 centimeter. And then we have to bring the beam out in good order and match it. So that's what all of these other solenoids are about. Okay. And so what happens is so what happens is we get a very we can get a very good transverse emittance reduction, but we get longitudinal emittance growth for exactly the reasons I was talking about. Now, the other game we can play is we can reduce the momentum. So if we reduce the momentum, then we can get to lower and lower beta functions at the cost of walking up this energy curve. So as we get to, this is the beta gamma here. So as we go to lower and lower momenta, we're going in this direction, which means that the heating, longitudinal heating term gets worse and worse. So we want to squeeze transverse emittance in the final cooling system at the cost of longitudinal emittance. Okay. And then I did want to mention this as well. I think Daniel mentioned it on Monday maybe, but as you squeeze the beam down more and more, your beam is drilling through an absorber, and it does drill through the absorber. So as you go down in energy, you deposit more energy in your absorber because the DDX curve pushes you up, and also your beam gets smaller and smaller, which means again you're depositing more energy in the absorber. So the energy per unit volume grows quite rapidly, and so you end up having boiling hydrogen, which causes trouble. Okay. So that's transverse emittance. What about longitudinal emittance? So we can reduce longitudinal emittance by using this emittance exchange scheme. So we have an initial beam which is narrow with some momentum spread. We go through a dipole, and what that does is it actually introduces dispersion into the beam. So that means that the high momentum particles will tend to see a thicker part of the wedge. The low momentum particles will see a thinner part of the wedge. And so what we end up doing is we end up actually exchanging emittance between the transverse phase space and the longitudinal phase space. So we're reducing the longitudinal emittance, but at the cost of increasing the transverse emittance. And this process on its own does not reduce emittance at all. So in the maths, what we're doing is we're actually our energy loss expression becomes dependent on the transverse distribution of the beam. So I'm going to introduce this dispersion factor, which is like the amount of the correlation between transverse momentum and position. And so you end up having this extra term, which is the dispersion times the density variation with position. That's the amount of longitudinal emittance reduction. The cost then is that you get a long transverse emittance going up, or you get less cooling because you've moved emittance from transverse phase space to longitudinal phase space. Okay, so we use this emittance exchange scheme in the rectilinear cooling system. So we have 6D cooling here, and the way we do it is we actually have dipoles and solenoids. So in the cartoon I said, well, we do a dipole then a focusing element, but actually in reality we do everything all at once. So we have a dipole superimposed onto a wedge absorber with RF cavities in the same place, and we get an optical beta function which looks like this. This is the solenoid field. The absorbers would typically be liquid hydrogen if we can, or lithium hydride, and we have very careful shaping of the solenoid field because we're worried about these stop bands. So this is, for example, how the transverse focusing looks, and you can see that there's these stop bands at 2 pi, stop band at pi. This is the beta function as a function of momentum. This is the beta function as a function of momentum. Sorry, that is momentum on the horizontal axis. You can't see that. So so there's actually 2 different types of lattices we use. So we use the A-type lattices, which operate in this pass band, and we weaken the magnets a bit so that the acceptance is around about 200 MeV over C, and then we go into the B-type lattices where we induce this resonance, and we can operate in this regime. Okay, so in longitudinal we have RF cavities, which Daniel covered the other day, but I wanted to show you what the sort of longitudinal phase space looks like. So what I've got here is I'm gradually increasing the thickness of the absorbers. So here I have no absorber, and I'm sending particles round and around a stable point. And so you can see the edge of the bucket here. This is the particle which is just about on the separatrix. And this is just a stationary bucket. So there's no acceleration going on. There's no absorber in place. Now, as we put a bit of absorber in, what happens is the particles lose energy in the absorber, and they need to regain that energy in the RF cavities. So what happens is the synchronous phase, the stable fixed point, moves a little bit, so that this particle here is the particle which exactly regains the energy which it loses in the absorber. And the other thing you'll notice is that my particles are looking a little bit there's a lot more noise in the distributions, and that's just caused by energy straggling and all of these longitudinal physics processes which we talked about, all the energy loss processes in the absorber, which causes this is like a heating effect, or it could be a cooling effect depending on where the balance lies between longitudinal emittance and transverse emittance. As I make the absorber a little bit thicker still, what happens is the stable area gets smaller, and this point here actually gradually moves forward in time because I need more accelerating voltage. And eventually, when I'm near to 90, this is the 90-degree point. When I'm over here, I have only a very tiny area which is stable, and most of my region of longitudinal phase space is not stable, and there are no particles there. Okay, the other thing is in this system is the dispersion. So dispersion is the correlation between position and momentum. So what I've got here is I've plotted the closed orbit, the orbit closed trajectory for 3 different momenta. So I have the lowest momentum particle as the blue dashed line, the highest momentum particle is the green dashed line. And what you can see is that by introducing these dipoles, so this is a dipole field, the dark green line is a solenoid field, there's a dipole field, and because my particles are not going along the axis of a solenoid, there's also some radial field component from the solenoid itself, which is where most of the curvature in this plot is coming from. That induces this transverse displacement, which is momentum dependent. I have I'm showing 2 different configurations of dipole here. In this configuration, I have a positive dipole, then a negative dipole, then a positive dipole. And you can see that the dispersion vector flips every meter, every time the dipole field flips. In this configuration, I'm showing a dipole field only in one direction, and you can see that the dispersion is always in the same direction, always in the horizontal direction. But it's much weaker. And so we somehow, there's an active discussion of whether which one's the right one to do. Do you want the weaker dispersion, but all in the same direction, or do you want the stronger dispersion, which flips? And then this is the cooling performance for the rectilinear cooling system. So I talked about matching earlier. So, well, first of all, you can see the red curve shows the longitudinal emittance reducing. The black curve shows the transverse emittance reducing. This is what we want. And there's 2 different sections, one with the passband A and one with the passband B. What you'll see is there's these little spikes. It's exactly what I was talking about earlier with the matching. So we haven't correctly matched in especially longitudinal phase space between different parts of the system. So you actually get mismatch, and that causes emittance growth. You'll see here this in passband in this region, you actually see evidence of little spikes in transverse as well, which again comes from poor matching between different bits of the lattice. Okay. So good. So Elias, you talked about collective effects, but I put the beam loading slide in as anyway. So maybe you have it in your talk, or you. Yeah. So the other, and one of the main issues we're dealing with in the rectilinear cooling system is that we have beam loading. So that means that the muons, as they go through the cavity, induce an EM wave, and they also have their space charge voltage, so their intrinsic voltage, which also degrades the voltage produced by the cavity. So this is this plot shows in dashed black line here, you have the nominal voltage from the RF cavity, and then the blue curve shows the voltage you have when you include all the beam effects. Yeah, so the red curve shows the voltage induced by the bunch, and you can see that there's the degrades performance. One can repair the performance, but it means increasing the voltage quite significantly. So going from sort of 2 volts maximum voltage to sort of 5 volts maximum voltage, so almost more than doubling the voltage to try and repair the longitudinal RF. Okay. Oops. Right. So I think I'm potentially on time. So I hope so. We went through second moment invariance, talked about particle amplitudes, talked about matching, and then I looked at the transverse cooling equation and this intrinsic longitudinal heating, which we get, and then I talked about the longitudinal cooling equation and emittance exchange. And so the final cooling, it actually comes after the rectilinear cooling, but somehow it's simpler, is just a transverse cooling and a longitudinal heating system. And then the rectilinear cooling, which actually comes before the final cooling, but it's more complicated, actually uses this emittance exchange technology to reduce both transverse and longitudinal emittance. So what I'm going to talk about this afternoon, I'm going to go through actually the muon production system, talk about how we glue the bits together, and then I'm going to talk about some of the alternative cooling schemes out there. Somehow this is the baseline, and I'm going to talk about other ways of doing it.
In heating, I think I kind of have two questions. The first is, are we saying heating in terms of just going through an absorber or in the process of absorbing reacceleration, absorbing reacceleration? And then the second is that I think you went through the maths, but I still didn't quite understand why it's heated longitudinally.
Okay. So RF cavities are actually emission conserving objects. So so you can't cool using an RF cavity. That people sometimes talk about a concept called geometric emittance, which is an invariant only if you're at the same momentum. And then that geometric emittance will change as you change momentum. But the normalized emittance, which is some sort of fundamental quantity, you know, if you like Noether's theorem, then it comes back to Noether's theorem and things like this, then that normalized emittance is actually conserved even in an RF cavity. So the absorber is the bit which does all the cooling. Okay. And the heating, in fact. So let me go through it again. So if I have a, I can draw it on the board potentially. So I'm going to have a beam. This is time. This is energy. So this is my beam. Okay. So now I'm going to deal with the plot on the left to start with. So I have a particle here, and I have a particle here. Okay. So if you look at the Bethe block curve, the particle down here is actually the one which loses more energy. Okay. So this one's going to end up after the absorber down here somewhere. The particle, the higher energy particle, is this one. This one's going to lose less energy, so it's going to end up it's going to end up here. And so if I draw the ellipse, or if I can draw it, the new ellipse is actually bigger than the older ellipse. The area is bigger, and emittance is the area of the ellipse. You happy?
And the one with the higher energy loses less energy because of where we are on the beta block curve?
Exactly.
Okay, thank you.
And there is a, you know, you can in principle cool up here. The rectilinear cooling channel works around this region where it's not such a big deal. There's a weak longitudinal cooling effect if you're over here because the energy loss is in the opposite direction, but it's too weak to really be very useful. There's another ingredient though. So there's this side now. So I'm only going to consider that energy straggling just to simplify things, but I'm going to do the same plot and do the same thing. So here's my time, energy. So now if I lose energy, so let's say if all the particles lost the same amount of energy, we get down to here, yeah. But there's a little bit of energy spread, and the uncertainty adds in quadrature. The energy spread from the energy loss adds in quadrature to the energy spread inherent in the beam, just like sort of noise from a detector or something like this. So you end up getting a bit of a spread in energy from that. Okay, so that's also an emittance growth effect.
Thank you.
Okay.
Those are. I have a follow-up.
Sure.
Two questions.
Great.
One is which. Can you hear me? Okay. One of which is, can we compensate for this energy spread by changing the phase in the RF cavity that we're using to accelerate after the absorber? And the other question I had is, in the final cooling, you mentioned doing it at lower momentum. How much lower momentum, and is it enough to impact the muon lifetime in the lab frame?
So let me deal with the second question first because it's easier. So let's say the rectilinear cooling operates a bit below minimum ionizing. So you have a momentum of about 200 MeV over C, 250 MeV over C. So gamma is about 2, relativistic gamma, you know, maybe 1.5. Final cooling operates with gamma 1, typically. So yeah, so there is a difference in lifetime from the time dilation, but it's a factor of 1.5 or 2. So it's not a huge effect, but it is there. The particles are going slower in the final cooling as well. So for a given distance, you tend to get more decays. So that's the easy question, right? So then you said, can you reduce the spread in energy using an RF cavity? And the answer is, I didn't go through longitudinal optics, but actually it's the same as the transverse. What RF cavities will do is they let you rotate your beam. They let you do symplectic transformations, and symplectic transformations, as we've seen earlier, always conserve emittance. So actually this thing symplecticity comes from the Hamiltonian. So I sort of tried to, maybe you can even see it, right? So it comes back to this, right? So this symplectic condition really comes from anything which is described by a Hamiltonian. So any physical transformation will be a symplectic transformation. And so as you told me, you collectively told me, symplectic transformation conserves emittance. So therefore, any electromagnetic thing will conserve emittance. And what's really going on in cooling is we're actually doing something quite fundamental. We're moving entropy, heat from the beam into the absorber, so into another object. And so that's sort of fundamentally, we're doing something quite special, which you can't do with an RF cavity.
Thank you.
Okay.
I had a question about the beam matching. So it seems very important and also very hard, right?
Yeah.
Because you're trying to place things very specifically in this nice pattern in phase space. Is that like well understood how to do that? And if so, is it a very lossy process? Like, do we lose a lot of nuance in that? Or can you just talk about that a bit?
So people spend a lot of time worrying about it. I mean, you know, when you're going from one subsystem to another, yeah, you know, typically you will need, for a generic accelerator component, you will need tens of meters, hundreds of meters of equipment to actually get the beam so that it's in the right orientation, so it fits into your next bit of accelerator correctly. So indeed, that is a tricky problem, and people do worry about it quite a bit. Now, if you're in luck, you're in sort of the nice part of the phase space, like this part where it's sort of fairly elliptical and everything's well behaved. Once you start getting out to, well, this one, if you're out here, you're probably in trouble, you know. So it depends on the system, of course.
Cool, thanks.
I think you said that you do the rectilinear cooling just at the lower momentum of the minimum ionizing point.
So
Of the beta block.
This one.
Yeah. So I would have thought that being just to the right of it would be better, because then you lose more energy for high energy particles. So yeah, why do you not do that?
So that's what you say is correct, except the rate at which you cool is proportional to, it should be on this formula, it's like dE over E. So somehow, if your energy is huge, then your rate of cooling becomes very low, and you need more and more equipment, and it gets very expensive. So somehow there's a compromise in terms of cost and that level of optimization, which tends to push you to be around minimum ionizing, but maybe a little bit below. The benefit you get from being on the other side of the minimum this minimum ionizing bump is not so strong, because it's a logarithmic scale, so it's actually a very slow growth.
I see. Okay.
Go on, Dave.
Equation you showed.
Oh no, did I get
I
it
was going
wrong?
to make a comment. The one with the dE dz over E, that one.
I think I copied it from your paper, Dave, so.
Well, yeah, okay. No, the last one, not that one, the one you showed just a second ago.
This one?
Yeah, that one.
Uh-huh.
If you look at that, it's at, the units are actually more correct if it's dP dz over P, where P is
Okay.
momentum.
Yeah, no, fair
So
enough.
that properly gets in various relativistic
Yeah, yeah.
factors, and it's, that you can, yeah. Anyway.
Yeah, yeah. Yeah, I mean, and I guess it's fair to say this is beta gamma, so this is like P over M. So, you know, there's a factor of beta, relativistic beta, which becomes important down here. You know, over here, of course, beta is 1.
Okay, I think we are getting more and more precise.
Good.
Thank you very much. Cooling, unfortunately,